Have you ever watched an ice skater start a slow, elegant spin and then suddenly pull their arms in and become a dizzying high-speed blur? And you just think, how in the world did they do that? Well, it's not magic, it's physics. The physics of spin. And today, we're going to break it all down. I promise by the end of this, you'll see it's not some complicated trick. It's just a different way of looking at motion. Let's get into it.
But first, a question to kind of get your wheels turning. We've all been there, right? Trying to balance on a bike that's standing still feels completely impossible. But the second you start moving, it becomes stable, almost effortless. What's going on there? Well, the answer to that bike puzzle and the secret behind the ice skater, it's all wrapped up in the physics of spin. And here's the best part. If you already understand how things move in a straight line, like a car driving down a road, you're basically halfway there. All we're going to do is learn how to translate what you already know into a new language, the language of rotation. So here's our game plan. We'll start by turning a simple push into a spin. Then we'll figure out how to find an object's perfect balancing point. After that, we'll dive into that new language of rotation, and we'll meet the rotational versions of mass and force. Then we'll put it all together to finally understand how those skaters spin so incredibly fast. Okay, first things first. Before we can talk about how things spin, we need to know what is doing the spinning. And in the story of physics, we always have a main character. In physics, we call it a rigid body. Now, that sounds super technical, I know, but it's just a fancy way of saying we're talking about something solid, something that doesn't bend or squish or change its shape when it's moving around. Think of a bowling ball or a spinning top or even a planet. And this slide shows exactly what I mean. We're keeping it simple. We're focusing on solid objects, like a bar or a disc, that move and spin as one single piece. We're not getting into complex things with hinges or bendy parts. For our purposes, it's just one solid, rigid object. Now, every single one of these rigid bodies has a special point, kind of like its physical heart. And this point is absolutely key to understanding how it moves. So, let's find it.
This special spot is called the center of mass. It's this one unique point where we can pretend the object's entire weight, its entire mass, is all concentrated. And this is a hugely useful idea, because instead of having to track the motion of every single atom in, say, a spinning wrench, we can just track the motion of that one single point. It makes everything so much simpler.
So where is it? Well, for any simple, symmetrical object you can think of, like a perfect sphere or a block of wood, the center of mass is exactly where you'd guess it is, right in the geometric middle. It's the object's perfect balancing point, its heart. And when an object is spinning freely through space, it will always spin around this one point. Okay, so we have our object and we know how to find its center. Now for the really cool part. This is where we learn that new language I was talking about. We're literally going to translate everything we know about normal, straight-line motion into the world of spin. Now this table right here, this is our Rosetta Stone. Don't worry about the Greek letters, just look at the concepts. On the left, you've got stuff you already get. Velocity is how fast you're going. Mass is how much stuff you're made of. A force is a push or a pull. Well, on the right, you have their direct rotational twins. The big idea here is simple. For every concept in linear motion, there's an identical one in rotational motion. We're not learning new rules, we're just learning new words for the same rules. Okay, let's zoom in on the two most important new terms on that table. These are the rotational versions of mass and force. If you can get a good feel for these two, I promise everything else will just click right into place. First up, moment of inertia. So, in straight line motion, mass is what we call inertia. It's an object's resistance to being pushed. A heavy bowling ball is way harder to get moving than a light tennis ball because it has more mass, more inertia. Well, moment of inertia is the exact same idea, but for spinning. It's an object's resistance to being spun. But here's the crucial difference, and this is where it gets really interesting. An object's mass is just what it is. It's a single number. But its moment of inertia is way more complex. It doesn't just depend on how much mass there is, but on the object's shape, and most importantly, how far that mass is from the point of rotation. To make this super clear, let's compare two shapes. On the left, we have a ring, and on the right, a solid disk. Let's just say they have the exact same mass, and they're the same size. But look at where the mass is. In the ring, all of that mass is way out on the edge, as far from the center as it can get. In the disk, that same amount of mass is spread out all over.
And the math backs this up completely. The formula for the ring's moment of inertia is its mass times its radius squared. But for the disk, it's 1/2 of that. So what does that mean in the real world? It means the ring has twice the resistance to rotation. It is literally twice as hard to get that ring spinning as it is to spin the disk, even though they weigh the same amount. It's all about where the mass is.
So if moment of inertia is rotational mass, what's rotational force? Well, that would be torque. A force is a push or a pull. A torque is a twist. If you've ever used a wrench to tighten a bolt or turned a doorknob or pushed on a revolving door, you've applied a torque. It's the twist that causes something to start spinning, stop spinning, or change its spin.
Okay, we have all the pieces. We have our rigid body, its center of mass, its resistance to spin, which we call moment of inertia, and the twisting force that makes it spin, which we call torque. It is time for the grand finale. Let's solve the mystery of the ice skater. The secret to that incredible increase in speed isn't about the skater pushing off the ice harder or anything like that. It all comes down to one of the most fundamental, most elegant, and most powerful laws in all of physics, the law of conservation of angular momentum. And there's our last new term for the day, angular momentum. You can just think of it as the total quantity of rotation an object has. And the formula is simple. You just multiply the object's moment of inertia, its resistance to spin, which is I, by its angular velocity, its actual spin speed, which is omega. Now here is the key. The law of conservation says that for any spinning object, as long as there are no external torques, no outside twists acting on it, its total angular momentum, L, has to stay constant. It must be conserved. It cannot be created or destroyed. The universe just won't allow it. Okay, let's put it all together. Picture the skater. She's spinning with her arms stretched out wide. Then she pulls her arms in tight to her body. By pulling all that mass closer to her center of rotation, what did she just do to her moment of inertia, I? She lowered it, right? She made it easier for her to spin. So if her total angular momentum, L, has to stay the same, and her inertia, I, just went way down, what has to happen to her spin speed, omega? Exactly. To keep that equation, L equals I times omega, perfectly balanced. If the I part goes down, the omega part must go up to compensate. She trades her resistance to spin for pure speed. It's not magic at all. It's just this beautiful, real-world demonstration of a fundamental law of the universe playing out right there on the ice. And this isn't just for skaters. This one law explains how a ballet dancer controls their pirouette, how a gymnast controls their tumble, and even how a giant dying star collapses into a tiny, incredibly fast-spinning neutron star. It is a universal balance. So from the bike that's stable because its wheels are spinning, to the skater who becomes a blur, my final question for you is, what else is spinning out there, all around us, held in perfect balance by this one beautiful law? Something to think about. Thanks for joining me.